Hello everyone, this is Ruizeng Li from University of Science and Technology of China. I'm glad to present our work, Interactive Editing of Discrete Chebyshev Nets. Discrete Chebyshev nets are chord meshes with all edges of equal length, which are inextensible along the edge directions. They have been widely used in many fields, such as architecture, packaging, and art. Since such nets are very useful in practice, it's desired to design them in a short time. However, if we want to regenerate a new Chebyshev net by deforming the original triangle mesh, it takes lots of time and may violate the user's design intentions. For example, the singularities which are colored may not be placed at the desired positions. Our goal is to edit discrete Chebyshev nets via a handle-based interface interactively. There are three basic requirements. First, the mesh after editing is still a discrete Chebyshev net. As an approximation, we require the maximum difference in edge length to be small enough. Second, handles reach the positions specified by the users. Third, the editing process is fast enough to achieve an interactive rate. There are two main challenges. First, we need to constrain edge length directly. That's different from isometric constraint, because deforming discrete Chebyshev nets has shared degrees of freedom. We show a figure here. The results all preserve edge length by different methods, but they are quite different because of freedom on sharing. Second, constraining edge length is a nonlinear and non-convex problem, so it's challenging to solve this optimization problem at the interactive rate. Let's review previous methods at first. Salkin and Mark construct local rigidity energy to describe the isometric constraints, but that's different from edge length constraints. Boazes et al. Uses local global solvers to solve shape constraints, but it cannot constrain the maximum edge length deviation to be very small, as we show in the bottom figure. As for geometric optimization, Sheldon et al. Adopts the framework to deal with the minimization of composite objectives, but it doesn't solve the edge length constraints. So there is no previous technique satisfies all requirements. Next, I will introduce our method in detail. Our input includes a discrete Chebyshev net, handles, and their target positions. We hope that after deformation, each handle reaches its target position, and the edge lengths remain unchanged. Since the second requirement is strict and too hard to meet, we use a soft constraint energy function and let it approach zero as an approximation. We use the infinite norm to define a constraint energy function, which can describe the maximum edge length deviation. Due to the non-C1 continuity of the infinite norm, it's difficult to directly optimize the L sub maximum to approach zero. Since LP norm with a large P is a good proxy to approximate the infinite norm, we adopt the LP norm to define a new objective function. However, we observe that optimizing this function needs many iterations to obtain a small dl submaximum in our experiments. Therefore, we construct another new objective function, which is based on the following inequality. As shown in the figure, the new function decreases much faster than the old one near our target. We plot the new function with different p's. When p gets larger, the decreasing rate gets faster. We construct the new objective function, and we found that optimizing the new function is more effective than optimizing E sub p. Our problem can be formulated as a constraint optimization problem. Our method relies on a second-order solver. After getting the inputs, we first compute a Hessian matrix of the energy function, which is further modified to be a positive semi-definite matrix. This is the main step of our method. Second, we consider the linear constraints of the handles and solve the KKT system to compute the descent direction. Third, we perform a backtracking algorithm to determine the step size. Finally, we update positions of vertices and judge whether terminating the solver or going to the next iteration. Since our objective function is the sum of the energy on each edge, we construct the modified Hessian matrix by computing on each edge. We propose a novel convex modulator for our objective function. First, if a function can be decomposed as a sum of a convex function and a concave function, then we can construct the modulator and minorizer of the function at a point x sub 0, and they satisfy following properties. First, the modulator is convex and the minorizer is concave. Second, their values and gradients at x sub 0 are all equal to the original function. Third, they can constrain the value of original function globally. If a function has the composite form, and composite functions all have convex-concave decompositions, then we can construct their modulators and manorizers. If the modulator of outer function can be further decomposed as a sum of an increasing function and a decreasing function, which are all convex. Here, increasing or decreasing is with respect to each variable when all the others are fixed. Then we can construct a function which can be proved to be a modulator of f. In our method, the beginning steps are similar to Sheldon et al.'s, but the further decomposition and modulator are different from theirs. For our objective function, we can decompose it to a simple form and construct the convex modulator. Then the modified Hessian is computed as the Hessian matrix of the modulator. Now I will revisit the method of Sheldon et al. It constructs its modulator by constructing modified inner functions. Our modulator is different from theirs, and our solver provides another way to construct a modulator. We have the following proposition for the differences between the two modulators. Although this proposition shows our modulator is greater than that of Sheldon et al.'s, we think a tighter modulator cannot guarantee better global performance in theory. That's because tighter is more local and tends to be more effective when near the global optimum, but it may lead to insufficient decrease when far away from the global optimum. We found that Sheldon et al.'s modulator considers influence of g depending on value of partial derivatives of h. For our function, since g sub e is convex, it doesn't use value of g sub e when h is decreasing. We propose our decomposition to take the Hessian of g into consideration in this case. Our modulator uses the further decomposition regardless of the value of gradient h. Actually, our method can have the same modulator as Sheldon et al.'s by choosing some special decompositions. But by choosing different decompositions, our method provides a different way to construct modulators. Here are experimental observations. We define a measure ρ to record the proportion of edges that satisfy L sub e greater than L, and we color those edges to be pink. As shown in bottom right figure, their solver tries to make L sub e greater than L for all edges. When that is satisfied for most edges, the energy and the L sub maximum drop suddenly. We conjecture the reason is when L sub e is smaller than L, it uses the Hessian of g sub e, which is 0. Consequently, their solver uses many iterations to remove the influences of the lost Hessian. And such process leads to noisy results. Despite the noise, the result is also a discrete Chebyshev net. The different results are caused by the freedom of deforming chord mesh with only edge length constraints. We present more examples here. Our method is faster and does not generate noise in practice when L sub maximum is bigger than 10 to the power of -6. We propose two speed-up strategies to accelerate the optimization. The first is adaptive P strategy. We observe that the value of P significantly affects the convergence rate. A small p leads to a rapid decrease of the L sub maximum at the beginning, yet cannot penalize it to be very small. A large p produces an opposite behavior. We propose an adaptive p strategy, which uses a small p at the beginning and adopts a large p in the process. The second is adaptive variable reduction. We observe that the age length deviation of most ages will be tiny after several iterations. It indicates that these ages do not need to be optimized in the subsequent iterations. So we optimize all vertices at first. Then we collect the vertices of specific ages and their n-rings into a set. Finally, we optimize the vertices in that set while fix others. Using this strategy reduces the optimization time and generates almost the same result. With these two acceleration strategies, our optimization procedure contains three stages. The first is optimizing all vertices using a small p. The second is updating all vertices using a large p. And the third is optimizing the selected vertices with a large p. Here we show a demo to demonstrate that our method can achieve editing discrete Chebyshev nets interactively. Next, I will show our experiments. In the adaptive P strategy, the values of P affect the convergence rate. In general, the small p is set to be 2. Different large p values are tested. We observe that larger p leads to faster convergence. However, a very large p usually causes numerical issues in practice. Hence, the large p is set to be 50 by default. We test 3 parameters in our workflow with more options. Since the results are similar for most parameters, we set them as shown. Our method contains 2 acceleration strategies. Here we perform an ablation study to show how each strategy improves the convergence rate. 4 methods are studied as in the form. It shows that both strategies contribute to optimization acceleration. We select 4 methods as competitors. The first one is an isometric editing technique. The AREP energy of Sorkin and Mark can be directly used for code meshes. The second one is Boazes et al., which uses local global solver to constrain age length. The third competitor optimizes the following energy, which is the most natural form for preserving age length. In experiments, we choose p equals to 4 and 8. We use our solver to minimize it. The fourth competitor is solver of Sheldon et al. We use both acceleration strategies for the solver. From the comparisons, they cannot minimize the maximum age length deviation to be small enough. Our method succeeds in achieving a much smaller DL sub maximum using less time. Here we optimize E sub different with different p's. We found that increasing p cannot contribute to improve the convergence rate. Now I will conclude our work. Our method provides a novel approach to edit discrete Chebyshev nets interactively. To make the maximum age length deviation drop to be very small, we use LP norm to define an objective function. Then, the objective function is minimized by a second-order solver with a novel moderator. Consequently, our optimization method is able to reduce the maximum age length deviation quickly. The feasibility and practicality of our editing tool are demonstrated by successfully deforming various discrete Chebyshev nets. There are some future works which are not solved. First, large deformation or hard positional constraints of handles may cause the algorithm to fail, and the cause may collapse as we circle since we cannot guarantee isometric deformation. Second, when moving a point handle, it appears that the shape is globally affected, even if the vertices are far away from the handle. How to control this is an interesting future work. That's all. Thank you.